Good morning. I will start the presentation. Actually, this presentation will be preceded by two presenters, and there's a first presenter, Jin-Hyuk Jung, and he will in charge of the later part of our presentation. And I am Jin Lee. And our work is in DABiD, the powerful interactive Android debugger for Android malware analysis. Yes. Okay, first one is a reversing Android application. I think most of the analysts will acknowledge all those static analysis and behavior analysis and dynamic analysis techniques. So our work is based on Debugger. So I will just explain dynamic analysis. Is to conduct step-by-step debugging with disassembled text code. And in Android, there is a small debugging in ID Pro. So let me explain in more detail about DABiD scalable debugging. So there's a small debugging. A small debugging use APK tool and DABiD in combination. And in this slide, I made an example using NetBeans ID, for example. So the analyst with this APK file, they disassemble application first by using APK tool and get hands of Smalley code. And this Smalley code is now can be used in a NetBeans project, replacing Java source code in a project, and also the to do the debugging, the APK file should be in a debug mode. So by using APK tool, the analyst should disassemble and also build the application in a debug mode. So now the analysts have a modified application, which is a debugger flag is true. And also they need to sign application with key tool and jar signer, and also install application on smartphone. And then the analyst executed application on the smartphone, and now by using NetBeans, the analyst can connect to the smartphone, the process, which is already running on a smartphone. So by putting on some debugging settings like JDWP host and port settings. ID Pro supports DABiD debugging from version 6.6, and basically it is similar to Smalley debugging, but uses its own text disassembler. So first of all, the analysts take same measure for the Smalley debugging. They need to modify application in a debuggable mode. So to do that, they use the APK tool to disassemble and build and signing process all over again. And also, they can just open APK file from ID Pro, and ID Pro gives a list of files in the APK file, and they can select the classic.txt file from ID Pro. Then ID Pro gives the interpreted view of a classic.txt file, and it gives a readable bytecode of the DABiD executable too. And also, the analyst should set debug options like package name and activity names, and they can start debugging from using ID Pro. Then ID Pro gives start application, which is installed in smartphone by analyst, and then this process is a way for debugger to be connected, and then ID Pro can continue debugging. So this slide compares Smalley debugging to ID Pro debugging. So basically, both debuggers need applications to be debuggable. It's just a default option for debugger to debug an application. And also, both debuggers requires debugging settings. In case of Smalley debugging, it requires JDWP socket and host and port information. And in case of ID Pro, it requires package and launchable activity names. And in case of DABiD executable disassemble, in case of Smalley debugging, it needs to be disassemble APK file by using APK tool to get Smalley code. And in case of ID Pro, it has its own disassembler, so it does not need manual code converting process. So up to this part, analysts should do those steps manually, like converting application debug mode. To do that, they need to use APK tool to decode and build and sign an application and install application, and they need to set those information for debugging settings, and they also need to disassemble text files. And also, I will explain more later about register type, but Smiley debugging gives the correct type of registers. I will just explain more later. And but IDA Pro convert every register casted as object. So in case of some registers which cannot be casted as objects, such as primitive types, they give bad fault error. And also in perspective debugging, debugging starting point is also different. In case of smart debugging, the NetBeans project can attach to the process which is already running on the process. So when the debugger is attached, the application already running on the smartphone. So the analyst cannot debug the previous instructions before the debugger attachment. But in case of IDA Pro, with this package and launchable activity names that is set from analysts, they start the application and set breakpoints at methods at runtable activity, and the process is wait for the debugger. So using IDA Pro, the analyst can start debugging from the start. But the main problem is that we want to talk in this session is the DEX used in debugging in both debugger is extracted from APK. But what if the DEX I'm debugging is not the one really running on smartphone? Okay, Blue Box Security, one day they posted a blog that proved that my fears can be realized, and Blue Box Security posted a proof of concept application that verified tampering DABiD bytecode during runtime is possible. And actually the application, when it is executed, as soon as it is executed, the log library and its good function, which write bytes into memory where the DABiD executable is loaded. So the function find the code item of add method from DEX loaded in the memory, and it writes bytes into code item of add method. The code item is a structure in a DABiD executable, which contains instructions of a method. Trying to do a little bit late. And there's another example that proves that APK, the classes.dex extracted from APK file is not the only target that we should analyze to. This example, Google App Store malware load encrypted DEX file at runtime. So even though analysts can obtain class.dex file from APK, but class.dex from APK has no malicious actions in it. It only has decryption and dynamic loading routines existing in class.dex. So there's no way to debug malicious code in it. So yeah. So I think from this point, I think we made our point. DEX can be different in memory, so the debugger should debug DABiD executable in memory. But the current analyst tools, they are targeting class.dex statically gotten from APK file, so analysis with current analyzer might be useless at some point. So now let me introduce our work, DABiD, Dynamic Android Binary Debugger. The goal of our project is to develop Android debugger which is able to debug the same DEX running on memory. And also there was some bothersome presetting jobs, and there are some things that should be advanced in debugging. So we aimed for making Android debugging more effective and convenient for analysts. To achieve our main goal, we monitor dynamic changes in memory and reflect them to debugger. And in case of in perspective dynamic changes, we thought two changes in here: self-modification of DEX byte memory and also dynamic DEX loading. And to achieve our second goal, we provided advanced debugging features, which is code update by analyst and register value acquisition. And also we automated bothersome setting jobs for Android debugging. So this is an overview of our work. Basically, it resembles Java debugger structure. It has text disassembler, which is disassemble text file from both APK and in memory. And also there is a debug event handler, which create and handle debugging event from JDWP. But using JDWP has limitations in perspective of reverse engineering. So we made our service module reside in application process during the lifetime of the application. So this DABiD service module notifies supervision results of dynamic changes in memory and also give a control over the application. So let me explain in more detail about our main goal, monitoring dynamic changes. And first one is about self-modification of text bytes. And DABiD service module, which is reside in the application process, it detects the memory write function call is made and alarm debugger when event happens. When the write function is made, then DABiD service module prepares for the information that debugger might want, such as byte stream and destination address of write function. And the DABiD interpret the message and alarm the analyst where in the text bytes is differentiated and let analysts to change those parts. And analysts are now able to analyze hidden bytes, dynamically change the parts. The second one is dynamic text loading. DABiD service module find and dump new text bytes in memory. When opening text method is called, and DABiD service module manager gives the order to DABiD service module to find and dump new text. Then DABiD service module browse memory and list up all the texts in the memory and compares the list of texts the list of it already have. So there, by do this comparison, it finds new text and dump the new portion of in the memory and gives it to DABiD service module manager. So and then debugger interpret the new text and give a clean view of the text in a debugger. So with DABiD, analysts no longer need to find the location of hidden or newly downloaded texts, and also do not need to conduct static analysis for new texts by pulling them to local. Okay, this is for our second goal, advanced debugging feature. And this one is a code update by analyst. So analysts can modify bytes code on the fly. And analysts can select instruction from our debugger and can put input bytes. Then DABiD service module, which is in the application process, it writes input bytes to proper location in memory, and debugging runs with modified bytes. So analysts are able to first to execute code by inputting goto instructions in the part of instructions, and also can skip code part to insert no instructions which is not should be executed to continue analysis, such as disrupting debugger or sending information to command and control server. And this is for register value acquisition. JDA provides register values only with debug symbol, but not all registers have debug symbols. So this is a table of simple example. There's some simple Java instructions, and it is compiled to bytecode a little bit longer instruction we see in here. But when we see this bytecode, there's a V0 to V3 registers are used, but only V0 have debug symbols because Java assigned int A to V0. But But in debugger, we need to provide all registers values and all registers information. So we modified JDI to get values and register. First of all, we did in a disassembling process. We created debug symbols by pre-emulating instructions. And also we eliminated evaluation check whether the register is visible variable or not, because for debugger, V0 is the only one which is visible. The other variables, V1 to V3, is not visible yet. So we eliminated evaluation check and cast the value with the type information gotten from DEX disassembler. And also we automated some debugging jobs. DABiD automated the following things to a debugging. First one is transform application into debuggable. Remember the previous debuggers used the APK tool to make an application in debug mode. So we transform application into debug mode in our debugger, and we also install application to start application. And also we set JDWP socket connection automatically. And also we set breakpoints at starting point of application, and application is waiting for our debugger to be debugged. So we can, using our debugger, we can debug from the start point of the application. So now we will show you our work demonstration, and this will be conducted by Jinhyuk Jung.
Before we begin, wait for ready, please. Where is it? Okay, let me show you a demo. Before we begin, I'll introduce the UI on the screen briefly. This is DABiD in development. The composition of a UI is simple. Package and class width on left side, code viewer on center, breakpoints and variable viewers on right side. Okay, I'll show you 3 features of our debugger. The features are debugging code dynamically loaded, debugging code dynamically modified, and modifying the instruction while debugging. First, I'll show you debugging code dynamically loaded. I open the app created for this demo. It's quite a simple app. It just loads external classes and execute it. Okay, let's start. When the debugging is started, debugger sets up the app and analyzes the ODEX extracted from device memory. It takes a little bit of time. Doing it now. Okay, it's finished. After it finishes, the app stops on the entry point. Entry point. And I'll set a breakpoint at the instruction next to the class loading instruction. Is the screen is small to display the whole code. Wait. The instruction is here for loading external classes. So I will set a breakpoint here next to it and continue the execution. It takes time for loading classes. Please wait for complete. Okay. Now debugger takes the dynamical loading classes and inform to user there is a new one. If I select the yes button, then debugger extract the new ODEX from memory. You can see the new package and class list loaded by main activity class. It's here. Okay, let's see. As you can see, the class new one. And then I will set the breakpoint at the method called by main activity. The method name is a task. Then I will continue the execution. Then now it hit the breakpoint. We are able to debug dynamically loaded code, and we can stop here. And you can see the register value is on the right side. It's changing according to code position. Here. Okay, next I will show you debugging self-modified code and modifying instruction while debugging. Terminate it and for this demo, we'll use the blue box POC app as you well know. It also takes time to analyze ODEX when I start the app. Okay. After launching finished, you can see that the execution stopped at the code of a loading library, and which is to modify some code by calling read map function. Okay. Oops. The code is calling load library, and next calling read mem function. Okay. Then this function modifies the add method, as you said, of string class. Add method is just calling length method literally. Let's look. Let's see it. As you can see, this function just calling length method literally. Okay, let's resume the execution. Oh, sorry. Then, if the debugger detects the modification of code, then it informs of the modification, and so we can apply it on the disassembled code. Yes, it's finished, and okay, I'll resume the execution again. Then it stops on the entry point on create method of main activity. Okay, let's see add method again. You can recognize that the code has been changed. Now it's calling several methods. Seems like doing something. Has maps and string to char. Okay, I'll set a breakpoint here. And let me make them being called. Okay. Then you can see the execution stops on add method. So we can debug self-modified code and stepping it on this code. But in this method, the conditional jump instruction won't be taken because V3 is not less than V7. V7 is 0 and V7 is just 0. So jump won't be taken. So the method will be returned, but we don't want to return it. So I will change the instruction to no instruction. And then let's stepping. So the method one, you can see that method didn't return and continue the execution. Okay, demo is over. Let's back to slide. Oh, sorry. As I said, the tool is in development, so we will focus 3 points as our future work. Oh, sorry. Just future. First, we'll deal with the art. Now, Android suffers art as a default platform. It has the different architecture. So there will be appeared protection techniques using art. And second is code coverage. Android app can include libraries, which is running on native environment, and malwares usually use them to make analysis hard. Third, we'll handle anti-debugging. We'll do that as possible we can, unless it is complicated issues on debugging. Okay, this is all we prepared. I thank for listening. Is there any questions? Yeah. Pardon?
The availability of the code, are you kind of private only at the moment? Are you willing to distribute it?
Not yet. We didn't decide yet. Yeah. Any? Okay. Thank you.